Hello, I'm Dr. Abhishek Sharma. In this video, I will discuss digital modulation technique, which is quadrature amplitude modulation. So let us start the quadrature amplitude modulation. First, to start with, I need to clarify the digital modulation, which is basically divided into two methodologies. One is baseband digital modulation and second one is the band pass digital modulation. The baseband digital modulation techniques are those techniques in which no carrier term is involved, but in case of band pass digital modulation methodology, this is a wireless transmission and an electromagnetic carrier signal is important to modulate the digital signal. Baseband digital modulation, there is no need to transmit wirelessly. I mean to say that this baseband digital modulation is a wired digital transmission. So in case of quadrature amplitude modulation, I want to clarify that quadrature amplitude modulation is a part of band pass digital modulation techniques. Basically, band pass digital modulation technique involves the baseband digital data first. There are several techniques like PCM, DM, ADM, DPCM, by which any analog baseband signal can be converted into digital equivalent, digital baseband signal. After the conversion, digital baseband signal can be transmitted with the help of carrier signal by changing the properties of carrier. So that's why I am saying that band pass digital modulation technique involves a carrier. This is a simple digital modulation block diagram: source, then source encoder, channel encoder, modulator, transmitter, channel, receiver. Transmitted signal can be transmitted with the help of antenna, and after that a channel includes the AWGN, which is additive white Gaussian noise, and after that composite signal, which is the transmitted signal plus the signal of noise signal, can be received by the receiver antenna, and after that demodulation and the reverse procedure, which will already happen at the end of the transmitter. So this is the reverse process. Now come to the QAM, which is quadrature amplitude modulator. The quadrature amplitude modulation, which is the QAM, utilizes both amplitude as well as the phase components to provide a form of modulation that is able to provide high level of spectrum uses efficiency, right? That means simultaneously we are changing two properties of a carrier signal. Number one is the amplitude as well as the phase component. So QAM, quadrature amplitude modulation, has been used for some analog transmission including AM stereo transmissions, but it is for data applications where it has come into its own. It is able to provide highly effective form of modulation for data, and as it is used in everything from cellular phone to Wi-Fi and almost every wireless high-speed data communication systems. In this pictorial presentation of a QAM signal, you can clearly see that if, let us suppose, this is an in-phase component, this is a simple carrier, then you can see that after the modulation there is a change in you can clearly see that this is the pi by 2 phase change. You can see that at this point to this point you can see that 0 to pi by 2 and then pi, right? If I am talking about the sine wave, then you can clearly see that. So from this point to this point is shifted to that point, right? So you can clearly see that there is a phase shift at this for this wave, right? Quadrature amplitude modulation is a signal in which two carriers shifted in phase by 90 degree. That means, for example, if we want to transmit two different digital bits with the same frequency component, that means in that case I have to take a single frequency component but two different signals with the phase difference of 90 degree. For example, let us suppose that AT is a first data stream and BT is the another data stream. Then if I will modulate, like as this is a quadrature amplitude, so amplitude is already been there in the nomenclature of QAM. So you can see that if I have applied the output of the oscillator, right, local oscillator, from that let us suppose I am applying cos of 2 pi fct and I have received an amplitude modulated, that is ASK. Let us suppose if this is a binary data, then I will definitely get BASK, right? But now, point to be noted, there is another, let us suppose this is a pi by 2 phase shift, right? That's why I'm saying so. This is 90 degree. When you apply in the pi by 2 phase shifter, and you will definitely get what? Sine of 2 pi FCT, right? With the same frequency component. When you applied the BT bit stream, right? And you will get definitely B of ASK, but for different digital bit stream. But you can simultaneously transmit these data with the help of wireless methodology. Now, point to be noted that you are sending 2 bit stream or 2 data with the help of same frequency, but these 2 frequencies are separated with the help of pi by 2 phase shift, right? So as a result of their 90 degree phase shift difference, they are in quadrature, and this gives the rise to that name, quadrature amplitude modulation. Often one signal is called the in-phase or in-phase signal. So for example, when I am applying this cos of 2 pi FCT, so this will be in phase, right? And that will be the quadrature phase, right? Quadrature. So that's why Q is here, right? Quadrature amplitude modulation, QAM, may exist in what we are termed either analog or digital form, right? So that means QAM can be the part of both modulation methodologies, like analog modulation, yes, definitely it belongs to the amplitude modulation category, as well as digital modulation. So this is also related to ASK, right? So the analog version of the QAM are typically used to allow multiple analog signals to be carried on a single carrier, right? That's why I'm saying in the previous slide I have already shown that AT is a single is a one data stream, or you can say it may be a digital data or be analog data, and this will be the another data stream or another analog data, right? So these AT and BT may be anything, either it belongs to the analog or digital. So to multiple analog signals to be carried on a single carrier, yes, definitely there is a single carrier which is FC, but these two terms are separated by pi by 2, right? So if you draw the spectrum, then you can see that at FC is a single frequency component here, because in if you are drawing the spectrum with the help of CTFT, then you will only see the magnitude. If you are considering the magnitude, then you will only see the single frequency component. But if you apply the phase spectrum, then you can clearly see the differences, right? So for example, it is used in PAL and NTSC television systems, where the different channels provided by QAM enable it to carry the component of chroma or color information. In radio applications, system known as CQAM is used for AM stereo radio. Here the different channels enable the two channels, and one is important stereo to be carried on the single carrier. Digital formats of QAM are often referred as quantized QAM, right? Quantized to be noted, and they are being increasingly used for data communication, often within radio communication systems. Radio communication systems ranging from cellular technology, as in the case of LTE, through wireless system including WiMAX. Wi-Fi 802.11 uses a variety of forms of QAM, and the use of QAM will only increase within the field of radio communication. So I want to conclude that that 4G and 5G, right, 4th generation and 5G generation of the communication already included QAM for different scientific reasons, right? Quadrature amplitude modulation, when used for digital transmission for radio communication applications, is able to carry higher data rates than ordinary amplitude modulated schemes and phase modulated schemes. Basic signals exhibits only two positions, which allow the transfer of either a 0 bit or a 1 bit. Using QAM, there are many different points that can be used, each having defined values of phase and amplitude. This is known as the Constellation Diagram. So Constellation Diagram is basically a representation. I have already told you that in phase component and quadrature phase component. You can for example, if a point is here, then the difference you can say the distance from the origin will represent the energy of that bit or symbol, and the angle, this angle represents the phase difference from the in phase component. That is the constellation diagram. Although QAM appears to increase the efficiency of transmission for radio communication system by utilizing both amplitude and phase variations, it has a number of drawbacks, right? So the first is that it is more susceptible to noise. Why it is more susceptible to noise? Because of this amplitude content, right? Because the states are closer together, so that lower level of noise is needed to move the signal into a different decision point, right? Receivers for use with the phase or frequency modulation are both able to use limiting amplifier, right, that are able to remove any amplitude noise and thereby improve the noise reliance. This is not the case for QAM, right? The second limitation is also associated with the amplitude component of the signal. When a phase or frequency modulated signal is amplified in a radio transmitter, there is no need to use linear amplifiers, whereas in QAM that contains an amplitude component, linearity must be maintained. So for this reason, the circuit cost will become higher. Unfortunately, linear amplifiers are less efficient and consume more power, and that makes them less attractive for mobile communication. It is showing the QAM demodulators block diagram. You can clearly see that at this point I am just installing my antenna, receiving antenna that receives the transmitted QAM signal, and then BPF, band pass filter, which actually eliminate the noise other than the center frequency, right? This is which will be FC. Then ADC, which is the analog to digital conversion, and after that the same process, oscillations. This is the single frequency component, and then match filter with the alpha and a switch that is used to sample the incoming signal, and after that the decision making device which delivers the resultant demodulated data. Other than this, a simple demodulator circuit is also representing. With the help of this diagram, you can clearly see that the input bit stream is received with the help of the antenna, and then a splitter divided into two parts, right? And after that a mixer is used, that is nothing but the product modulator, which is also used, which was actually also used in BASK. An oscillator, that oscillator generates the same signal like 2 pi f of ct, and 90-degree phase shift means sine of 2 pi fct, right? So this is the in phase component, and you can also demodulate the quadrature output. So the point is, if I conclude the QAM, then quadrature amplitude modulation, in simple, you can actually use single frequency component. With the help of pi by 2 phase shift, you can transmit two different digital bit streams on a single frequency component. Similarly, you can also demodulate the same content with the help of the in phase and quadrature phase component, as I have already described this in this slide. So in this video I have described quadrature amplitude modulation. Thank you very much.